Hello and welcome back to Calculus 3 for one last time, right? That's it. Made it. Green's theorem today. We are going to take a look at this really interesting way to compute line integrals. This is one of the convenience methods. Is it necessary for survival? No. But if the conditions are right, we can use this to calculate integrals much faster. For instance, you would remember a convenience formula maybe from Calculus 1 where we said if you have odd function on a symmetric interval, answer is 0. Right? That was a convenience formula. Do you have to know it? No, because you can go and you can compute and you will get 0 at the end. So now we learned how to compute the line integrals in 14.2. We call that, right, line integrals the long way. And then we learned about conservative vector fields last time, and we learned how to find the potential function. So we know that the line integral over the curve C of f dot dr was our line integral. And we had a method to compute this line integral by dotting the vector f, which is the vector field, right? And then we have AB, dotting that with r prime dt. Right? That was not the magnitude. It's r prime of t. But now we can think about f being the gradient of some potential function phi, which is what we learned last time, and then we plug that in over here. So now my line integral f dr becomes the line integral delta phi.
We're all standing outside. We didn't know lecture was on.
I taught you a lot. Delta phi dr. And if we learned anything from fundamental theorem of calculus, we learned that integrals and derivatives cancel. Whew. Well, that's a fundamental theorem of calculus. So we can actually understand this as phi of point B minus phi of point A, which actually is the fundamental theorem of calculus for line integrals. So I'll write that here as the line integral of delta phi dr is equal to phi of B minus phi of A. These are the endpoints. And I'll box this, call it fundamental theorem of line integrals. So A and B are endpoints. I'll just put that A, B are endpoints of the line integral. So this is all built up on the old stuff. And now we would like to take a look at the fast way of computing line integrals. So if we have all of the conditions satisfied, we can have Green's theorem in circulation form and in the flux form, right, to compute the line integral over the vector field. And the two forms obviously will depend on the situation that you have. And as I said, it's a convenience thing. It's much easier to compute, shorter to compute, than computing the line integral. You know what you have to do for line integrals, the whole page, right? You have to figure out parametrization, then you have to find, which gives you your r, then you have to find r prime, then the magnitude of r prime, then you have to convert the function in terms of the parametrization, you have to figure out the limits for t, you have to plug everything in, then you have to integrate, right? So it takes time to do line integral problems. So Green's theorem is going to give us these two formulas, which are convenience method, right? Faster way to compute line integrals, but only if the conditions are satisfied. If you remember maybe from your Calc 2 class, if you wanted to do the integral test, you were able to do integral test only if the conditions were satisfied, and conditions were function had to be continuous, had to be positive, and had to be decreasing. So now you're going to have conditions, and if the conditions are fine, you can work on the integral. So let's go with the circulation form first. So this is theorem. Let C be a simple, remember that word from last class, closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane assume that the vector field F given by Fg, where F and good F for G have continuous first partial derivatives in R, then, and here is the theorem, we put the closed circle there, we talked about it, FDR, don't forget the arrows for vectors, it's going to be the integral of f dx plus g dy and this is the punchline now. Partial g, partial x minus partial f, partial y dA. What? Right? Line integral on one side, double integral on the other side, equal in between. Well, is this dimensionally okay? What is the dimension on this side? You have integral of a function. Well, that's function times the dimension. It's 2D, right? On The other side, what do you get? How does this make sense?
First integral cancels out the
Yes. One integral will cancel the derivative, so you have integral of a function. It's the same. You see, these formulas have to make sense dimensionally. So we do have the same situation where area equals area. We do know on a double integral with something inside, it's a 3D. But now that something inside happened to be the derivative, and derivative cancels the integral. Very good. So we do have everything work out dimensionally in this formula. Now, if you look at the shopping list of requirements, observe what you must have. You must have closed curve. And that should immediately make sense, because you are setting up a double integral over a region. You can't have that spilled to infinity. You can't do this over a parabola that it just opened up forever, because you have to close it, right, in order to get the number you want. It's immediately divergent, infinite, right? So you have to have a simple closed curve. It's not intersecting itself. Piecewise smooth. Edges are allowed. Square is fine. Circle is fine as well. Parabola intersected with a linear line. It's fine, because it's piecewise smooth. Meaning, piecewise smooth is for the duration of the function. You don't have sharp corners, and then when the two of these would meet, right? So if you talk about half a circle, you have a half a circle and then a straight line going on the bottom. It could create two corners. That's fine. We can deal with that. Oriented counterclockwise, fine if you end up with a circle. You just need to make sure cosine is first for x. That encloses a connected and simply connected region. Connected region means one piece. Simply connected means no holes inside. Well, those are all of the regions that you had. And technically, what this theorem does is transforms your line integral, it's pain in the neck to compute, to a simple area integral, double integral that you learned in 13.1 or 13.2, like the first two lectures. Right? Maybe you get the polar 13.3, but it's a basic double integral. So let's take a look at a problem. Instead of working a problem for 7 years, we can simply just draw the domain and set up the double integral instead. And that's the power of Green's theorem. So you can be literally done in 2 seconds. This thing over here is called a two-dimensional curl. That's the name, the two-dimensional curl. And if the curl is 0, we say that the vector field is irrotational. Does not rotate, right? Because the curl is 0. So if curl of f is 0, we say that the vector field f is irrotational. What does it mean, irrotational? No spin, yep. Good. So, do we remember that our rotational field should give us a value? Do we all remember that? So let's do the same problem, where we have our vector field to be negative y comma x on unit circle. right? So now, let's think about all of the prerequisites, and you're running this in your head. Is the circle closed? Yes. Is the circle smooth? Yes. Does it outline the region which is one piece? Yes. Does the circle inside have a hole anywhere in the area? No. Right? Do y and x have first partial derivatives exist? Yes. So all of the criteria for us to use this Green's theorem, all the criteria is there. So all I need to do now is to calculate curl, which is that partial g, partial x minus partial f, partial y, compute that, and integrate that over a region we have. So curl of f is going to be partial f, partial y, which is -1, minus the other one is also 1 to get -2 for the curl. Once I have the curl, I just need to plug... no, sorry, I was supposed to do partial g, supposed to be partial g, partial x. Partial g, partial x is 1 minus -1, so it's +2. Much better. Sorry. Partial g, see it's partial g? Partial g. G is the second over here in the... Alright, good. So now, I have a circle. What is the double integral for the circle? Well, hopefully polar coordinates, right? So, I have a double integral of 2 r dr d theta. Theta is 0 to 2 pi, and r is 0 to 1, it's a unit circle. So, when I integrate this, I get r squared, 2 and 2 would cancel, from 0 to 2 pi, and I still have d theta to deal with. This is 0 to 1. So now I'm integrating 0 to 2 pi of just 1, which is d theta, and there's your 2 pi. It's the same answer that we have, but remember how we had to chase the sines and cosines and plug everything 5,000 times? You remember that from the last class? Or last week, whatever we did it? Now, with this, you compute the curl. As soon as you compute the curl, you plug that in, and that's it. Let's take a look at one more example from homework. I think they give you 1 or 2 more examples in the book. You can read that. Let's go look for circulation. All right, so how about a triangle with vertices and stuff like that? Problem 14. We have vector field f given as -3y, 3x, and R is a triangle with vertices 0, 0, 1, 0, and 0, 2. This is our problem. What do we have to do this problem using the line integral? We have to do 3 separate problems and add them together. You have to run the line integral for the line that stretches from 0, 0 to 1, 0. That's a full problem from 14.2. Then you have to restart the problem and do for the piece from 1, 0 to 0, 2. And then you have to restart the problem again to go from 0, 2 back to 0, 0. because there are 3 lines. There are 3 different c's, and each one of those warrants its own integral, right? So that would take 3 pages, right, of calculations. Because you have to come up with parametrization for each one of the line segments. Then you have to go, that's your R, then R prime, and all of the stuff that you did. And you have to restart every time, because every time you do the C, you have a different parametrization, which gives you different R prime magnitude, and all of that integration from scratch every single time, right? Maybe you can fit that in 1-page calculations. They shouldn't be that long. There are no sines, cosines, and things like that. But it's long. It's 3 separate integrals. Green's theorem says, do we have a closed line? Yes, we do, because triangle has the perimeter closed. Do we have piecewise smooth? Yes, we have 3 linear lines. They're all differentiable. So that means smooth, right? We do have corners, but that's what a piecewise is for. You are not allowed to have absolute value x. Because that is not smooth, because within the function there is a spike. You can break it apart and still deal with it, but yeah. And the region is connected and simply connected because it's a triangle. It's one piece, that's a connected, and then simply connected, no holes, right? We learned that last class. These guys have the f and g, have the continuous first partial derivatives. So, all of the conditions for us to do Green's theorem circulation form are have been met. So what I need to do is to compute the curl of f. Curl of f is the partial derivative of 3x is 3 minus partial derivative with respect to y of f is negative 3. So it's 6. So curl is 6. And then I need to draw the region so that I can set up my double integral area. And we're done. So I have to go and say, let's use 2 units for and then 1 unit over here. There we go. So here's my triangle with 0, 0, 1, 0, and 0, 2. All right, pen, come on. You can do this. So to set up double integral, they don't care how you set up your double integral. They just say that the answer for the line integral and the answer for the double integral, whether it's rectangular, general regions, or polar, whatever double integral you can master for chapter 13. Well, we're going to use dy dx. We know we need to stick the curl inside. So we have dy dx. X goes from 0 to 1. And y goes from 0 to this linear line, which is 2 minus 2x, right? Y-intercept is 2. Slope is negative 2 over 1. So 2 minus 2x. Now, that's a joke to compute very quick. So, Green's theorem, as I mentioned, is a convenience method to calculate line integrals. If you break any of the conditions, you are not allowed to use Green's theorem. You have to go back and compute each piece. So if the region is not closed, if there are any weird things happening with functions, not smooth or anything, any condition that it's broken, you cannot use this. Integrate 6, we get 6x, so that's going to be 12 minus 12x, right? Because it's just 6 times that. And then when we integrate this, we get 12x minus 6x squared from 0 to 1, which is 12 minus 6, which is 6. And there we go. Why, are you disappointed?
Is it just a coincidence that the 6 in the 6 as our curl is 6 is the answer?
Yes.
Okay.
It's a coincidence because over here you have 2 and 2 pi, right? So, yeah. Flux form. Theorem. Same conditions. As circulation. Alright, so the pen is definitely dying over here. So the flux form, we remember that we are using the vector n. So we have f dotted with n ds is going to be dy minus g dx, which is the double integral over region R of partial f partial y plus partial g partial x. There we go. dA. No. This is a G. This pen doesn't want to work anymore. That's a G. There we go. Much better. So same conditions.
What is ds? Like, what is that to do with
ds is the parametrization in terms of the arc length, because all of these lines are curves, right? And you have the arc length measuring the length of the curve rather than measuring it with a straight dx or dy pieces. So when we do the conversion from ds, which we did the first time, I believe, when we did curvature, you jump from ds into dr, and dr is combination of x's and y's. Now we have this again, this piece that has a special name. Called the 2D divergence. And we say that if divergence is equal to 0, then the vector field is source free. Please remember that for the flux, you are measuring how much stuff radiates out. So if there is no radiating out, that means that within that vector field, there is no source to make stuff radiate out. You have to have a source in order, right? Sun has to be there in order for the radiation to radiate out. The light bulb has to be there in order for light to come out, right? The fan needs to be there in order for the wind to go forward. So now we say if divergence of F equals 0, we say that the vector field F is source free. So there's nothing inside to generate radiating whatever you're measuring. So to create wind between 2 points in space, I don't know, Somerville and Branchburg, you have to have a difference in pressure, in air pressure. And then the air will flow from which one to which one to equalize it. High pressure to low pressure or low pressure to high pressure? High low? Low high? I'll keep my poker face until someone explains why. Okay. To equalize, good. All right. I don't know if you guys realize, but all of those concepts are the same. You know, you have low pressure, high pressure to move the air. You have higher height and lower height to move the water, right? Because the water will always go downhill. And then you also have potential, which we call voltage potential in the outlet for the current to flow from. This is all the same. It's all the same. Just like all of the fields, magnetic, electric field, gravitational field, they all weaken with the square of the distance. Right? It's the same formula for force between charges and gravitational force between two planets. They just involve a different constant. Right? So all of that stuff is always the same. All right, now, so for our flux, we remember that the radial field was the one that gave us the answer. So let's take the introductory example for flux form of Green's theorem to be the radial field xy on the unit circle again. And we calculate the divergence first. So divergence is div f. Divergence f is going to be just 1 plus 1, which is again 2. We're calculating divergence there. And then we know that the unit circle, right, we'll use polar coordinates again because our curve C and the region R inside. So to calculate, I'll just use the double integral of 2 r dr d theta, 0 to 2 pi for theta because it's the full closed circle, and then the radius is 0 to 1 because it's a unit circle. R dr d theta is the string for polar double integrals, so r is built in. And now we integrate same steps as before, 0 to 2 pi, we'll get r squared from 0 to 1 d theta, which is integral 0 to 2 pi of d theta, which is theta, plug in 2 pi minus 0, and there's your 2 pi. Same answer, obviously, we just use a different method to get it, Green's theorem, and there you have it. Now let's go and take a look at homework problem. There we go. So, let's do something that we haven't, like parabola in a line or something like that. There's a triangle, there's a square, there's a circle. We did the circle, we did a triangle for the previous one. Parabola, number 25. Vector field F is given to us as y negative 3x and R is bounded by, region R, bounded by y equals 4 minus x squared and y equals to 0. You know what, before I do anything, I'm going to draw my region. 1, 2, 3, 4, 1, 2, 1, 2. And then we close it on the bottom. Looks like a bell, right? 4 on top. And negative 2 and positive 2 on sides. Is the region closed? Is the region simply connected? It's connected. It's simply connected. The line is closed. Piecewise, we do have 2 corners. Don't worry about it. Do we have first partial derivatives for our f and g? The answer is across the board yes. Right? So, we are ready to calculate this. What are we going to get? 0. Why? Divergence is 0, sure, but you look immediately at the vector field, it's rotational. It's a form of a rotational field, right? Didn't we just have that the rotational field was negative y comma x, and then the radial field was x comma y? As soon as you take a partial derivative, you see divergence is 0, so the whole thing dies. But just by doing enough homework problems, you will immediately recognize this as a rotation, because x is in the place of y and y is in the place of x. It is a negative, so that gives it a spin, right? And radial fields are always x is in the place of x and y is in the place of y. I think this problem. So for those of you that are quick to recognize those kind of things and did enough homework problems, because some of it to pick up a pattern and see the pattern and use the pattern, you just have to do a lot of stuff. That's how you learn patterns. You're not going to most likely memorize and remember what I just said, right? And I definitely didn't learn it from anyone. It's just doing 5,000 problems along the way. So you will see immediately when you start doing this stuff. So my divergence over here of f is 0, source free. Double integral of blah over here is going to be 0, and we're done. Double integral, yes, you're going to have x goes from negative 2 to positive 2 and 0 to the parabola, and you integrating 0. It's done. Is it going to be 0 if you do the circulation form? No, right? So you have to know what you're looking for. You have to know your applications. You have to know your physics, right? These are just mathematical tools. They're completely pointless and useless if you don't put them in a context of what you need, right? And for that, you have to wait for your specific 4-level and 400-level courses, right, to use them. And obviously, I mean, none of this stuff is computer science. This is mainly going to be mechanical engineering, electrical engineering. That's where this stuff kicks in. In terms of like structural stuff, I don't think so, any of that, and none of this is. This is mainly mechanical and high-end mechanical and stuff like that. So that's that. Bye. Bye. Have a nice life.